So this is Unit 2.1, Formulae and Amounts of Substance, and in this topic we are going to be covering empirical and molecular formula. We're going to look at molar gas volume calculations, percentage yield, and atom economy. So today in this video we're going to look at points 2.1.1 and 2.1.2, so looking at the relationship between empirical and molecular formula and then calculating empirical formula. At the bottom of page 1 and the top of page 2, you have your SEA definitions for this topic. So these are definitions that we'll meet throughout the topic, but they're ones to learn off by heart, word by word. These are ones that SEA can ask you in their exams, and they're very fussy about the way you word your definitions. So we're going to be looking at these two definitions today for empirical and molecular formula. So there are two other definitions at the top of page 2, but let's get stuck in and have a look at empirical and molecular formula. So it's really important that you understand the definition of these two types of formula so that you know the difference between them and know what you're being asked to calculate or to quote in an exam, whether it's the simplest ratio or the actual number. And that's really how these two formula differ from each other. So a molecule will have an empirical formula and it will have a molecular formula. Sometimes those are the same, but really it is just all dependent on the number or the number ratio that the formula is representing. So with the empirical formula, what you want to be thinking of is the simplest ratio. Okay, so if I was thinking of empirical formula, I would think simplest ratio. So the definition is a formula which shows the simplest whole number ratio of atoms of each element in a compound. And we'll look at an example in a second. Whereas the molecular formula is a formula which shows the actual number of atoms of each element in a molecule. So you can see these definitions are very similar, and in terms of learning these definitions, I would just think of that bit in the middle as different and everything else is the same. The only other small difference is that the definition for an empirical formula ends in the word compound and the definition for molecular formula ends in the word molecule. But obviously for molecular formula that could end in the word compound, but it could be an element as well, so that's why it's the word molecule. So just think empirical formula, simplest ratio, molecular formula is the actual number of the atoms. Down below that in your notes, you have a couple of important points. Firstly, that molecular formula is the one that gives the correct molar mass, because obviously it has the actual number of atoms within a molecule, and so that will give us the correct molar mass, because we need to know the actual number of the atoms in order to calculate a molar mass. The empirical formula, as we said, it states the simplest ratio, and it could be the same as the molecular formula, but it may not be the correct one in terms of the number of each type of atom, and therefore we cannot necessarily calculate our molar mass from that. So let's have a look at a really simple example. If we had a look at ethane, now we haven't done much organic chemistry this year, but this is something you should have met at GCSE. Ethane is your second alkane in the homologous series of alkanes, so it has 2 carbons. So if I was to draw its structure off to the side here, its structural formula, I would put 2 carbons in a chain together with just a single bond between them because ethane is an alkane. So it has 2 carbons in a chain, and then how we build up alkanes, we'll come back to this in our alkanes topic, is that we need to make sure every carbon has 4 bonds. So you can see the carbon on the left, it currently has 1 bond, so I'll draw 3 more. And the carbon on the right has 1 bond at the minute, so I'll draw 3 more. And alkanes are hydrocarbons, which means they're made up of carbon and hydrogen only. So what I do is I just put hydrogens at the end of each of these bonds. So you can see from the structural formula that the molecular formula is C2H6. I have 2 carbon atoms and 6 hydrogen atoms. The molecular formula is the formula that gives us the actual number of atoms within the molecule. But what about the empirical formula then? Well, the empirical formula, remember, is the simplest ratio. So what I need to do is look at my number of atoms and think, is there a number I could divide each of those numbers by to get a simpler ratio? So your ratio at the minute is essentially 2 to 6. If I divide both of those numbers by 2, that will cancel down to 1 to 3. So essentially you're getting your simplest ratio, asking yourself, what could I divide each of these numbers by? So the empirical formula is then CH3, because obviously we don't include ones in formulas. So CH3 is the simplest ratio of all the elements, but it's not correct in terms of the number of each type of atom in the molecule. There are actually 2 carbon atoms and actually 6 hydrogen atoms, and that's indicated by the molecular formula. But as I said, sometimes the empirical formula is the same as the molecular formula. So if we think of methane this time, methane is your first alkane in the homologous series, so it just has 1 carbon atom. So therefore it needs 4 more bonds, and we put hydrogen at the end of each of those. So if we think of the molecular formula, which is how many atoms there actually are, we have 1 carbon and 4 hydrogens. If we think then of the empirical formula, which is the simplest ratio, is there a number I can divide those numbers by to make them any simpler? No, there's not. And in fact, if there's ever just one of any type of atom within a formula, then that's going to be the empirical formula as well, because you can't divide 1 by any other number to simplify it down. So it's just going to be CH4 as well. So sometimes the empirical formula will be the same as the molecular formula. So that is really point 2.1.1 covered from the specification, looking at that difference between empirical and molecular formula. And what I want to do in the rest of this video is have a look at how we find formula using moles. And generally this method is going to give us the empirical formula. Not always, but generally it will give us the empirical formula. So we'll look at some worked examples, but these calculations are quite simple. You will be told that you have a compound containing certain elements, and you'll be told what mass of each element you have within that compound. So the first step is that we must convert our masses into moles. Sometimes you're given the masses as a percentage mass, so you might be told that it is 20% this element, 80% another element. In which case you can assume you have 100 grams, because then your percentages become values of mass. So if you have 100 grams of something and 20% of it is say sodium, then you'll have 20 grams of sodium within that compound. So assume you have 100 grams and just take your percentages as mass values in grams. Number 2 then, calculate your mole ratio by dividing all the moles by the smallest mole value. This is a bit like our last step of determining the degree of hydration within a hydrated salt that we've been doing recently. And if your mole ratio comes out as a decimal, multiply all the mole ratios by the same number to get an integer value. Because obviously in a formula you don't have something like, say, C2.5H5. So what you would do if you got to a mole ratio of something like that, you would think, okay, well, let's multiply both of those numbers by 2, and I would get C5H10. And as we've already said, this method usually gives us the empirical formula. So let's have a look at worked example 1, following that method that we've just seen. So it says here, a compound contains 4.6 grams of sodium, 2.8 grams of nitrogen, and 9.6 grams of oxygen. Find the empirical formula. So we know that we have to write this in the simplest ratio. So if it was to come out as one that we could cancel down, then we would have to cancel it down. But generally this method will give us the empirical formula anyway. So let's think of our elements. We've got sodium, we've got nitrogen, and we've got oxygen. What mass of each do we have? We have 4.6 grams of sodium, 2.8 grams of nitrogen, and 9.6 grams of oxygen. And if it was in kilograms or tons, you would have to convert to grams in order to use your equation for moles. So to work out the number of moles from our mass, we're going to be using the equation N equals mass over RFM. So it's worthwhile writing down your RFM at this stage. So that's just 4 elements. This is just going to be equal to the relative atomic mass. So for sodium, our relative atomic or relative formula mass is 23. For nitrogen, it's 14. And for oxygen, it's 16. And you just get those values from the periodic table. Next step is then to calculate the number of moles, and this is really still step number 1 of our method from above. So we're using the equation N equals mass over RFM. So for sodium, that's going to be 4.6 over 23. For nitrogen, that's going to be 2.8 divided by 14. And for oxygen, that's going to be 9.6 divided by 16. So if you put those values into your calculator, and I'd encourage you to do this along with me. So if you don't have a calculator handy, maybe pause the video, go and get one and come back to it. So 4.6 divided by 23, that works out as 0.2. For nitrogen, 2.8 divided by 14 comes out as 0.2. And for oxygen, 9.6 divided by 16 comes out as 0.6. So we're on to step number 2 now, which is to calculate the mole ratio by dividing all the moles by the smallest mole value, because we want these values to be as an integer whole number ratio. So what is our smallest mole value? It's 0.2. So I'm dividing each of these numbers by 0.2. Again, put that into your calculator. 0.2 divided by 0.2 is obviously 1. And again, we see the same for nitrogen. And for oxygen, it's 0.6 divided by 0.2, which comes out as 3. So what's our formula then? It's Na, and we don't need to include the ones in formula. Then just N, because there's only one nitrogen. And then O3. So my formula is NaNO3. So this is sodium nitrate. And that is the empirical formula because it's in the simplest ratio. So that is your final answer. Now you don't need to set it out in a table like this. If I was to be writing this in an exam, I wouldn't take the time to draw a table or anything like that. But I would work underneath my different elements. So I would start off by doing Na to N to O and then work underneath that in the same way that we have done, but just to say you don't need to write out the whole table. But if you prefer to do that and you find that a handy way of setting out these calculations, that's obviously fine as well. Let's try another example. So look over to page 4 and work example 2, and there's something you need to be careful about with this calculation, and it just is to really show you that you need to be careful when reading the questions to make sure that you understand what they're asking and what your compound is made up of. So it says given that 1.06 grams of magnesium, so you can highlight that as your first element, combines with oxygen to give 1.77 grams of magnesium oxide. Find the formula of the oxide of magnesium. So it says there to give 1.77 grams of magnesium oxide. So that's the total mass of my compound. So if that's the mass of my magnesium oxide, then what I need to do is work out the mass of the oxygen. If I'm going to get my formula correct, I need to know the mass of each of the elements within the formula. So I'm not putting the ratio of magnesium to magnesium oxide, I'm putting the ratio of magnesium to oxygen. So I first need to calculate the mass of oxygen, and I'm simply going to do that by taking my 1.77 grams of my magnesium oxide and take away the 1.0 grams of magnesium. That leaves me with 0.71 grams of oxygen. So if we have 1.77 grams of magnesium oxide and we know that 1.06 grams of it is magnesium, then the rest of it, which is 0.71 grams, must be oxygen. And now we're ready to carry on with our calculation. If you want, you could pause the video at this stage, give it a go yourself, and then play the video again to check that you're correct, because it's important that your examples and your notes are completely correct. Or if you're not quite sure yet, you can go through another example with me. So at this stage, we would then put our magnesium in ratio with our oxygen. The mass of each, we've just worked out 1.06 grams of our magnesium and 0.71 grams of oxygen. The RFM of each, which is just going to be the relative atomic mass, is 24 for magnesium and 16 for oxygen. Work out then your number of moles, because I can't put my masses in ratio to each other, and I'm using the equation N equals mass over RFM. So for my magnesium, that's 1.06 divided by 24. and that works out as 0.044. And with oxygen, that's going to be 0.71 divided by 16, which works out again 0.044. If you'd kept these numbers a little bit more accurate, you would see their decimal place was slightly different after that point. So with magnesium at 0.0441 and with oxygen 0.0443, but these are roughly the same numbers too. 3 decimal places is going to be more than enough. Sometimes your mole ratio doesn't come out as exactly integer values, but if it's very, very close, then that's obviously fine. So your mole ratio, we divide by the smallest number of moles, which in this case, it's exactly the same. So we just divide by 0.044. And so that's obviously then going to come out as a ratio of 1:1. And so the formula of my magnesium oxide is MgO. So just be careful that you read the question carefully. Make sure you understand, have they given you the masses of the element, or have they given you one of the elements, and then you have to work out the mass of the other element from the total mass of the compound. And then finally worked example 3, we mentioned that sometimes the mass values are given to you as percentages, but in this case you just assume that you have 100 grams of the substance and then your percentages just become mass values. So in other words, take your percentage values as mass values. Okay, so it says an oxide of copper contains 80% copper and 20% oxygen by mass. So if we were to assume that we had 100 grams, we would have 80 grams of copper and 20 grams of oxygen. So let's go with that. You can really choose any value. If you wanted, you could use 200 grams, in which case you'd have 160 grams of copper and 40 grams of oxygen. But I don't know why you would make your life any more difficult, and just stick with 100 grams and your percentages convert straight to grams. So we're putting our ratio of copper to oxygen. Our mass is 80 grams to 20 grams. The RFM of copper, again, just get from your periodic table, is 64. And of oxygen is 16. Just make sure you use the relative atomic mass and not the atomic number, because that obviously wouldn't give you the right answer. Then you need to work out your number of moles using N equals mass over RFM. So for copper, that's going to be 80 over 64, which comes out as 1.25. For oxygen, it is 20 over 16, which again comes out as 1.25. Your mole ratio, divide by the smallest number of moles, which again in this case is the same, doesn't matter which you pick, doesn't always work out this nicely. But that will then give you a ratio of 1:1. So your formula is CuO. So make sure that you have those examples written in accurately and check that you've got the right values, so that you have good, correct examples in your notes. Again, you don't have to write out that table each and every time, but set it out in a similar way in the examples that you do. So what I would like you to do now is to complete exercise 1. So as you did with like your titrations topic, have a set of file pages at the end of this topic that cover your exercises. So write exercise 1 as your title, empirical formula, just so that they're all there and you can reference those when you're coming back to revise this topic. Do please show all your working out, just as you would do in your exam. So for these questions, as I say, you don't have to write out the table. You might want to just do something like C to H to O, write your masses and RFM underneath, or even just go straight into N equals mass over RFM, but do show some sort of calculation. So be that if you wrote N equals mass over RFM at the side, and then underneath your carbon you would be writing 52.2 divided by 12, because that's the mass divided by the RFM of carbon, and so on. Again, in question 1, you're given the percentage by mass composition of the compound, but you can just take those as values of mass, just assuming that you have 100 grams of the substance. So please complete the questions in exercise 1. It's pages 5 and pages 6. There are 6 questions in total, so please do go on to page 6 as well. And then what I'm going to get you to do is to mark your answers using the mark scheme or the answers that I upload. And I'll get you to submit your marked work to Teams. So you'll mark that first. I'll just be giving you the final answers, but it's important that when I look at your work that I see working out, so that I can see you haven't just written down the answers. So give those a go now, and if you're having any problems, then you can get in touch.